been finishing, I was in the diastrate time, which is the time it takes to escape from a cusp. Why this is important? It is important because it occurs in many situations. So I have 10-15 minutes. I want to finish this, and then to move on with the application to super resolution, how we extract information from super resolution trajectories. So this is for what we haven't done last week. So this is called the diastrate. So this is, again, we have done this last week, so I just need these few minutes to finish. Diastrate time. So let me remind you the basic steps. Suppose you have a small hole, you want to escape from this domain. You start wherever you want, and this is so these are the obstacles. So those are the obstacles. So you have a particle, and this is the absorbing part. How long it takes to escape from here? So this is your Brownian particle. It does whatever it has to do, and then when you arrive here, you're out. This problem is not a classical narrow escape because of the cusp. And the cusp made the contribution to the escape much longer than the classical law in dimension 2. So let me remind you that in dimension 2, when you have a cusp, I mean, you don't have a cusp, but you can exit through a hole which has no singularity, geometrical singularity. The mean first passage time to leading order is the surface of the disk, omega, log of 1 over epsilon divided by pi d plus O of 1. This is tau epsilon, doesn't depend where you started. So this is log. When epsilon goes to infinity, when epsilon goes to 0, epsilon here, this is the ratio of the absorbing to the total boundary. This is less than 1. And when epsilon goes to 0, it goes to infinity with log, which is really not that big. Here, what we are going to see today is that, this is what I want to finish, which we started last week. The mean first passage time is pi omega, which is the surface here of this domain. This is omega. This is dimension 2, divided by d square root. This is non-dimensional. This is epsilon divided by r, where this is the surface, d is the diffusion coefficient, like in here, epsilon is the size here, and r is the radius of curvature that you have here. R is the curvature radius. So this is significant from epsilon, log of 1 over epsilon to this. This is a significant change. So I can actually start by explaining the application, and then I'll come back how you prove this. This is a result that came out, as we've seen last week, from a new type of asymptotics. Because here you have a new type of boundary layer. The fact that you are in a cusp, you cannot apply the classical match asymptotics where you know the solution here or the solution there, and you just match. Because here you have this particular shape. And we could not use either the method. So match asymptotics is the method developed by Michael Ward at the University of British Columbia with his collaborators, Dan, and all of, Dan who is sitting here. And
I just want to say, I had very little to do with the middle 20 pages of every paper that we wrote up.
You mean 50 pages?
It's 20 pages once he's compacted it down.
Yeah. The problem is when I have to review them, I have to redo all the calculations.
I know, I feel very sorry for you.
And usually it's correct all the time.
Yeah. And by the way, he writes it correctly first time. It's just.
Yeah, this is his business. He knows what he's talking about. It's called professional. Okay, so we could not apply Green's function. So I will remind you the steps that we did last week, briefly. And now let me explain why this is important, where it comes from. And I'll give you some questions. So first of all, this came from a model. All right, so before saying this, so this is really motivations for these results. Motivation and remarks. So suppose you have a membrane of a cell which is covered by obstacles. So the notion of being covered and how you cover is not universal. But most likely, big obstacles are going to be the most important things. So suppose, and again, this is an approximation, that you have a membrane covered by large obstacles, and suppose those obstacles are placed on a square lattice. If you have can imagine all kind of lattices with all kind of shape, this is very well known for crystals. So then you can ask the following question. Given the size of the obstacles, the size L of the lattice, what is the effective diffusion coefficient? That is, you have a particle, any kind of molecule embedded, let's say a channel, protein, receptor moving in this, has to spend a lot of time here, especially this is very narrow, and from this we'll have an idea of how long it takes for this receptor to stay here. To move from one region like this to another region like this, so you can always then coarse grain your diffusion by a jump process. Say if you wait sufficiently long enough, this is what we started last week to discuss, you can look at the jump from this place to that place to that place. So at each position you have, let's say, you can jump, if you jump out, you have 4 possibilities. Right? So this is where this question came from. So how do we, so question number 1, compute, how to compute the effective diffusion coefficient, how to compute the effective diffusion coefficient depending on the density, of obstacles. That is what happened, for example, when, so R, twice R cannot be longer than L. But for example, you can ask what happened when this difference L minus 2R is epsilon, which is small, and how this will give us the information about the effective diffusion coefficient. Why effective? Because if you're under the microscope, and if you sample at sufficiently long time scale, you don't see all of this movement. You see a point here, a point there, there, and then you have a jump. You don't see the red trajectory. And the second part of the class is going exactly to study what can you extract about the trajectory, about the diffusion coefficient, when you only get information about the sampling point. You just sample of these purple points. Okay, so this, I'll give you the answer for the first question. What is the diffusion coefficient for this? So the mean first passage time for such of this domain, you can relate this to the effective diffusion coefficient. This is lambda L squared divided by 4. So this comes simply by writing a Markov chain, or when you jump between the 4 places. Lambda is the rate of jump, And the rate of the jump is going to be 1 divided by twice the mean first passage time, because there is when you're here, there is always a probability to come back. So the time to make a jump is going to be twice by symmetry. And lambda is this 1 divided by 2 tau, where tau is this. So this is the effective diffusion coefficient. And so this is what we found, that for this time tau, it goes like this. If the escape here is not big, then you are back to something that looks like a normal domain. And if it is very small, if the radius here is very small, you are escaping through almost a fully absorbing square. So then there are 3 cases where the mean first passage time is C1 for epsilon. So this is normalized epsilon, so L now is 1. So this is epsilon, so this is what we found numerically, this value, 0.1 to 1. This is then C2, and then we're going to take the first case when you are an intermediate case where you don't see really the cusp, because the absorbing part here is big enough. So this is C2, omega log of 1 over epsilon. And this was for epsilon between 0.55 and 0.8. And finally, you see the cusp. So C1, C2, C3 is because I usually do not remember the coefficient. C1, C2, C3 are the correct coefficient. So for example, it's here 1 over pi. Yeah, 1 over pi, and yeah, we should probably put D somewhere. And C3 omega square root of epsilon. And this is for epsilon less than 0.55. This is what we found numerically as a good approximation. So then you have to plug this into this effect. So tau is, you can connect, this is the rate of escape. And this is the effective diffusion coefficient that has been calculated. This is, for example, given in Schuss or many other people in 1980 in this book. So, in particular, for this regime, and this is going to be comparable to what Andrew showed about Smalding many some months ago. As now, let's use the case where you have a very crowded, if you're in a very crowded case, very crowded cell, then the mean first pass, the effective diffusion coefficient D. So if you just plug everything, it's D, the real diffusion coefficient, L squared divided by L squared minus pi R squared, L minus 2R divided by R, where R is with the notation of this. Which means that what is the curve of the ratio of dE divided by D that you should obtain as a function, let's say, of R? Something like this, where this goes to 0 with the square root. And Andrew showed exactly this graph using numerical simulations with Smalding. Right, and this is 1. Oh, this is not 1, this is this maximum ratio here that can be calculated. Yeah. And R is 0. Yeah, we cannot, all right. Yeah, so here this is something different, because this formula doesn't apply in this regime, because this is exactly the regime where. But, all right, so we have this behavior at this location. This is important that it goes this way. Okay, so then I'm going to give 2 exercises, and then I'll explain briefly the proof of these results. So exercise number 1. Is what happened in dimension 3. So you have a cusp. You're in dimension 3. What is the mean first passage time? Whatever is the domain. What is important is that the domain is symmetric with respect to this axis. So you have something that, for example, has a rotation. You have a cusp here. When you slice it, you have the same situation as in here. And so what is the mean first passage time to escape through here? So I'll give you the result. And so how to calculate this, if you're interested, the references are the following. So this is omega. Now this is a 3D volume. D epsilon to the power 3/2 multiplied by 2 multiplied by square root of r. Well, this is r. So plus, yeah. This is independent of the initial position. And epsilon here this is the absorbing part. Absorbing radius. Actually, this is epsilon is simply this because you have your rotation, so this is a disk of radius epsilon. So how do you prove this? This is by adapting the method I'm going to discuss. So now an open question, and this is something we don't know how to do. Open question is, what happens when here you don't have a cusp which is of order 2? Suppose you have something like, so the way the curve approximates the tangent can be locally written like y, a constant, whatever it is related to the curvature, x squared. But now, what happens if you take something of the form constant x to the power, let's say, alpha, for alpha bigger than 2? So this is locally, when plus 4x. So if you have this locally, what is the mean first passage time? How? The mean first passage time here depends on whatever power is of alpha. So this is so an open question. Find how as a function of epsilon and alpha. This we simply don't know how to use it because in the methods, which is based on in dimension 2 of what is called the Mobius transformation, what is very important is to have this power 2 approximation. This is open.
Why just alpha greater than 2? What about alpha is 1.5?
Yeah, you can also try.
There's no.
Yeah, that's a good point. Let's say alpha different than 2. Bigger, strictly bigger than 1. If we have 1, you have like a cone. This we know how to do. If you have a cone, if you have something at the so if you have a cone and if you have an angle, and if the absorbing part, let's say, is here, it's again log. But instead of pi here, you got alpha. Alpha is the angle. So when alpha is pi, you get pi. Otherwise, you get this. But this, we don't know how to do.
Can I just ask something? So,
Sure.
So when you're doing the original one that you know how to do, where it says exercise, yeah, that's the one.
Yeah, this is, oh, sorry. So
what
this,
you do, you go to cylindrical coordinates.
That's right.
And then do a conformal map with this Mobius transform.
that's right, that I'm going to explain now.
Oh, sorry. Yeah. Okay. Go
I will explain now the detail. Now this is just to tell you it was the motivation. Now I will, in 2 minutes, I'll explain how you do this. I mean, we did that last week. Just want to, I didn't finish one point that I want to finish. And yeah, so this is, so the references for this effective diffusion coefficient and how we calculated all of this approximation, this is myself, Jose Schuss 2011. This is PRE, Physical Review E, 2011. Then we did all of this. This is myself and Schuss. And this was in SciAm multi-scale modeling and simulation, I think 2012. And we claim here that we know how to do this. The statement is incorrect. Because I'll explain in a minute why it doesn't work.
I'm curious with that, your expressions for the mean first passage time, the middle expression, I would guess with a log is an intermediate asymptotics.
Yes, this is this one.
Yes, but I'm saying it seems a bit. Is there? Do you really get it in terms of the bounds are just some numeric, just some constants rather than some function of some other parameters?
Well, here we fixed L is 1.
Yeah.
So probably when you go to a normalized constant, you may have L in here.
Yeah.
Right? This is for the normalization
Yeah,
case.
sure.
But in general, we haven't looked in, I mean, what else can change? Everything is invariant by,
Yeah, no,
will vary with scaling, so this should be multiplied by L here when you go to the L, I mean, non-dimensional situation. Then, yeah, there is two more things that we did for, again.
So you haven't done any simulations to even,
Yeah,
in this case, alpha bigger than 2. Have you any speculation on what?
I mean, you mean by fitting?
Yeah.
We've done some simulation, I mean, we did some simulation, we didn't fit anything. I don't know, and it's, so, for example, when you have something that, okay, I can answer partially this question. There is something that also is interesting. There is in neuroscience a structure. Can I erase this part? There is in neuroscience a structure which is called a dendritic spine, which has a shape like this, which is connected, let's say, to whatever it is connected through a cylinder. Now, when this guy alpha goes to infinity, it's like approximating this with something which is almost flat. That's why I'm going to answer partially your question. So if this is almost flat, you have a structure like this. What do you think about what is the mean first passage time to escape? It took us 5 to 10 years to answer this question. It turned out that the mean first passage time here, so basically suppose you have the cusp. In principle, this should be the result if the length here is 0. So if the length is 0, this is what you get. If the length is not 0, what you get is L omega divided by pi a squared plus, and then so you have now, you expand this in this basis, like 1 over a, and then comes this term here. So a here, this is, I should put here epsilon. And then the second term of the expansion is constant divided by epsilon to the power 3/2 plus, suggesting that in the limit that alpha goes to infinity, that you get something that is almost flat here, you get something of power 2.
Yeah, so 2 minus 1 upon alpha.
Yeah, I don't want to speculate, but basically we are going to get something in between 2.
Fits 2 data points.
Yeah, between 2 and whatever we got from here, 3/2.
Yeah, 2 minus 1 alpha.
Maybe alpha divided by, yeah. Okay, this shows that by adding here these lengths here affect the mean first passage time and drastically, because this becomes the leading order term. When L goes to 0, then this is the leading order terms we have found it. So this was just to answer Kevin's question. All right, and so now another motivation, and again, I'll give the result. I'm not going to discuss this. If you have a synapse, and if you have, now suppose you're interested in the process of vesicular release. So you have here a vesicle that contains about 3,000 neurotransmitter. Which are molecules. They are important to open here the gates. When these molecules are free, they move by diffusion. They can bind here to a channel, a receptor, and upon binding, with a given probability, a flux can be generated. Now, how this open? For this to open, you need to have a calcium channel, and under some specific condition, which I'm not going to describe exactly, the channel is open, calcium goes in. Now, let's magnify this region. What you get is you get something like this. You have now a channel, calcium goes in, and suppose you are interested in how long it takes for the ion to go here underneath this ribon. You have a ribon which is going all around your vesicle. So this is the ribon. And now we are interested in how many ions are going to be exactly located here, because here there are protein of interest that upon binding, this creates the condition for this vesicle to fuse completely with the membrane and neurotransmitter to go through. Again, you have here mean first passage time question, 3D, not exactly covered by this, how long it takes to go to hit the surface of a ribbon. So this is the mean first passage time, tau, is, so I have to explain what is omega. So omega is the domain. And suppose this is a domain, the big domain where you are, divided by 4 pi epsilon, where epsilon here, this is the height of the ribbon. And so this looks quite at the beginning we saw that this formula could not be correct, because this is exactly the mean first passage time to a small hole. But the main difference here is that the surface of the ribon is epsilon, a constant, whatever it is, depending on the parabola here, it's a constant epsilon to the power 3/2. So this is the surface of the absorbing ribbon. This is then the mean first passage time it takes if you do not start in the boundary layer here. If you start sufficiently far away, this is the time it takes for a particle, an ion, to hit here this place. So again, I'll explain in a second the same ideas, except that the Mobius transformation to do this is different from the one I'm going to describe here. It's not exactly the same, because here there's a topology in the absorbing boundary there. It's not like a small disk, and this makes the problem different.